first thing we want to do, I think, is just go back and fix this code where we replaced all of these integers. We should make them generic and then specialize the type down here. So we're just going to start from the top. These ones are not going to change, but these ones are technically these ones can be generically typed, so let's do that. So this should be a B, a C, A, and then I think it's a B and a C. Oh, what we can do is do this and just look at the types. BCA, BC. Oh, makes sense. You have to be able to equate the A's, otherwise that's not going to work. Okay, so let's fix this one. This one should be, we're going to need that equal A again. This is going to be B, C, A, B, C. Okay. The show instances, I guess it doesn't matter. They don't have to be integer. They do need to be like, actually it doesn't matter. Just I forget the term for this, but there is a term for this where, you know, whether you have this as ABC or BCA, they're the same things, as long as you're not like putting them in the same type signature. There's a name for that. I don't remember what it is offhand. Alright, so this is probably B, C, A, E, B, well, either B, C, and then I think we need to say eq A again. Right, what are we making here? Yeah, we're making an A, so that's right. Here is B, C, no, B, A, C, A. By the way, I just kind of remember this, so. And then we're given a B, a C, and then we need to say eq A. Okay. A, B, C, B. We don't have any viewers right now, so I probably don't need to talk out loud, but doing that. B, B. Okay. So in Oh. Yeah, I guess that's a good point, because these things are just curried, right? So you can just get rid of this. And apparently this as well. Apparently those already have show instances, which is interesting, but a single function doesn't. I don't know why that has... Okay, so this is prop curry iso. I think it's integer, 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 to integer, to integer, to bool. Okay, this one has the exact same type signature. Just technically it's, well, it's not technical, exact same. It's just that we need to write it a little different. And actually, maybe we don't. We'll test that real quick. So this is what the type signature looks like up there. But I think this is curried. So can you just write this? No. It's the same issue. I had this issue before, and okay, so that's the right type signature there. This one needs to be either okay, so that one's right. Pretty quiet night so far. And then oh, I need to put surrounding parentheses around this. All right. Do we need to fix anything else while we're sitting here? We tested these ones, we tested these ones. I suppose we might as well test these ones while we're at it. I mean, we tested all the other ones, so let's just quickly write that one too. Prop. And then we'll continue. Oh, it's after this. Okay, so we'll leave this here and we'll stick this one in between here. So this is basically prop, prod, unit, so the way we did this before was basically compose the two functions and then look at the type real quick and use this to help us. So we're going to take basically prod. We're basically going to take this as input right here. So a unit, we're going to give it an, what are we going to give this? Oop, missing a colon here. Need to give it an a, and we're going to return a bool, and need ek, I suppose. So here we're going to get, wait, isn't this supposed to be, this has to be a function, so I think it's actually like that. F a, so we compose the function, apply it to a, and that should be equal to id f a. Buzzing, hang on. Yeah, right. That's the part I'm confused about. I guess we're actually just gonna be given this, and you're actually just gonna do this. But this has to be in parentheses because I'm using a $sign. Yeah, and that should be the right type. Okay. So then prod unit from a. So this one's going to take a and return a bool. Prod unit from. It's going to take an a. Going to say prod unit from dot prod unit to of a, and really this isn't an f, right? Before it was an f. This is really kind of a tuple. We'll use that, and here we'll use just x to denote some x. Id x. Okay, those are easy. So, and then these go here. Prod unit to prod unit from. But I have to qualify their types. Okay, so what's this thing taking? This one's taking integer unit to bool. This one's taking integer to bool. Okay, I think that's it. So let's test, and we should pass all the tests. Here we go. So we've passed all of our tests, which imply that all the isomorphisms that we tested in the book are actually isomorphisms. So that's neat. Next, we have another one. So what I'm going to do is put this up here for now because we need to do some code development here. So we're going to do this one. A times B to the C times B to the C. All right, so the result goes first. So let's do this. So we have A times B to the C is equal to C. A times B is this. Yes? Let's double check our notes here. Yes. A times B is that. I'm using X in some places and stars in some places. I suppose I'll continue to use X for times here as to not like mix my syntax. So now we have the other one. So A to the C times B to the C. So basically we're gonna have a tuple of C to A, C to B. This is, I wrote XE2, it's really II, but that's okay. We're gonna use, we'll use 2 and 3 in this case, even though they correspond to different exercise numbers, but that's probably okay. What's going on here? So we need to have a function that takes C to A, B, and turns it into C to A, C to B. From, and then we need C to A, C to B, C to A, B. Now, in this case, I think we can pattern match explicit. Well, maybe not. We'll just leave it like this. And then XE3. Okay, and then let's put the stub in here for the property. So prop X3 nope. XE3 2.XE3 from. Hey, what's going on, Ryan? How are you? Do anything fun today? I worked, so it was sort of fun. I got to do Haskell today, so that was cool. Basketball. Can't get rid of them. So what I like to do if I can't get rid of nerves is just run like a madman for a little while. Helps me empty my mind. But you said you play basketball, so that's pretty good. You know what's weird is it doesn't say I have any viewers right now. I don't know if that's just messed up. Is there does it say viewers on the actual Twitch screen? I'm using like an external bot. Ah, doesn't work. Unfortunate. Sorry. Okay, so we have to define these things. So it says 5? Okay, so this is broken. Also, high pick. I don't remember if we decided pick or peak, but I mean, college is hard, right? Like, it's not super easy. All right, so we're gonna have an F, and what do we want to do with this F? For sure, yeah. There's nothing easy about school. Wait till you get to the point where you start thinking about grad school. I think that happens to a lot of people. That's even worse. That's not helping your nerves, so I apologize about that. Yeah, that's all you gotta do. So anyway, the viewer count thing is broken, so if you're around, say hi. I'm here. That's fine. So I think in CS, do you just get like an internship or something? Why did I shut this? Like in your sophomore or probably junior, senior year, you try and get internships and go from there? I assume that's what you do. I don't actually know. Good. With who? If you don't mind me asking. So I feel like I have to do something with first and second here. But what? Well, the real question is, if I remove these, do they still compose? I'll read that in just a second. Because if they do, it's a ton easier if they still compose. Yeah, see, they don't compose this way. Well, wait, confused. Why does it put the parentheses in there? Maybe no, I think... Yeah, I think I have to do something with fmap here, but I'm trying to figure out what. Because fmap is just composition, right? So if I just compose first with f, so I'm trying not to just write stuff and get the answer. Sorry, let me read this here. Oh, that's good. Yeah, Murph, I think you're right. I think you're right. And yes, I am technically a professor. I'm an assistant research professor. That's my title. So we just need to flip it. Wait, how does flip work again? Flip takes the first two things. That's not flip. It's like first, but backwards. I would. I don't. To be fair, I don't teach a lot of classes. Yeah, we can try that. Yeah, it's almost like this. It's just backwards, right? Like it's the other way. But I don't know how to. Yeah, it's close to that, Murph. I'm gonna go with Murph. It might be. I'm gonna go with a silent PF for Murph. Oh yeah, this is open over here, so it's just gonna bring me there. Murph works good. Let's Google this because there might be a function I've not ever heard of. That's true. So we have a C to A, B. Yeah, see, this looks a little problematic. What if we write A, B? Actually, let's write A to B to B to A. Op? O to N, N to O? They have to be new types. I don't know what that means. Op? This is not a linked list. Oh, viewers are working now. So, hello 5 people. Hope your day is going well. Apparently, there's more bots on Twitch than I ever knew, so maybe that seems to be a thing people talk about. Reverse the type of packer. This seems like it's too complicated, right? Not the problem. Just seems like this is not what we're looking for. Has anyone used this function before? Oh, let's try it. It doesn't look right to me, but I could be wrong. So let's try this. Well, some people, I think that, yes, well, I mean, so am I. I actually don't know what I'm doing. But anyway, like the point is that I think this is exactly the same because, right, fmap is just composition. But this is C to A. Oh, actually, yeah, it is this. It's this. But is this the same or no? I thought it was. Yeah, these are the same. Yeah. Because, yeah, for functions, compose or dot is the same as fmap. So you can write it either way. I don't know if it's more clear in this case to just write dot. But yes, this works. So why? Yeah. Yeah, but that's the only way you can do it. It's not that we're not f mapping the tuple, right? We're f mapping over the function. We would actually have to f map to get into the tuple to mess with B pick. In this case, f map is this. They're the same operator, but I don't see it yet. I'll probably get it in a second. Yeah. Yep. You're right, Murph. So if we did fmap here, then we could play with this B, but we don't have a function that can mess with B, so we would have to create one, I suppose. we can't really create one, but you know what I mean, I think. So why does this work again? So first, let's go look at types. We can figure this out. I don't see it. Oop, I have to do f equals. Can you guys read this okay? Just let me know if you can't read it. We are, I guess we are partially applying this. Wait, right? Is that right? Yes. Yeah. So we're building partial applications to say C. We're applying the function f to get an AB and then applying first. I'm just dumb, apparently. Right? This function will be applied to C to create AB, and then we'll take the first value out of it. And same thing here. Sorry, I'm just stupid. My apologies. So this one is a fib. And then you know, I have this weird feeling like this is gonna work. And I want to just type it and see if my brain is, nah, butts. I was hopeful. It's probably, it's gotta be more complicated than that. Everything's more complicated than that. So we're gonna be given a C. So we need to make a function, C. And then I mean, that's the right type. If you've got foo, yeah, if I remove, yeah, this is the right function, but I feel like there must be a way to write this. There must be a cleaner way to write this, but I don't know what it is. I think what you need to do is a bifunctor is the other way. Like if I had wait, how does bimap work again? A to B, C to D, PAC. No, it's not bimap, I don't think. I feel like there's a function for this that's a lot cleaner than what we're doing here. I don't remember what it is. Let's see if we can find it. No. What if we just put Haskell in front of this? I mean, I know this is the right answer, but I just wonder if there's a better way to write this. The only thing I can think about doing is just like removing the tuple altogether and writing just f here, but then you have to use first and second, so it's gonna look funny. It's some sort of like distribution function, like if you had like a bunch of f's. It's almost like apply, but apply doesn't work here because if you were to use apply on a tuple, I think you're doing like we were talking about earlier, functor only operates on the second half of a tuple. So here you kind of have an applicative, right? You have an f of a to b, but I don't think you can do anything with that. Let's just leave it alone. It's probably fine. We might be trying to do too much, which is possible. I do that a lot. Someone will come around and tell me there's a better way. They always do. Okay, so what are we trying to do for this property? So we need to look at the type of this and realize that we're going to get this back. So we need a function that takes this as input. So we're going to have f, and this is going to apply to f. And the type of f will be that, right? And then we need to apply this to a... What are we trying to return here? We're just trying to return two values. It's going to be similar to this. I guess we already tested this, didn't we? Sort of. So we're going to be given a C. So we're going to apply this to C, and we're going to say that's equal to id f C, sort of. Okay, the reason this doesn't work is because right, our actual type is this, so we need to do where G H, it's very similar to this other one, equals this thing. And then we will have basically another a prime is equal to G of C is equal to a prime, and H of C is equal to B prime. This is going to be first id f C. Oh, I need this. And B prime will be second id f C. There you go. Does this make sense to everyone? If you're having a hard time following along, let me know. Also, I think we can get rid of these parentheses. They're unnecessary. I added them back last time, but we don't actually need them. We had a bug last time where I had this type signature as like all integers, because what I need to do is eventually run this QuickCheck where we feed in the type signature. So if you plug in a type signature here, you don't get any type checking, not surprisingly, because A and B are both integers. Well, technically this is B and C. Maybe we should relabel those, but it won't be too much of a problem. But now we have type checking at least. So now this is actually a C, and this one is actually a B, whereas before they were both integers, so you could just like flip-flop them as much as you wanted to. Oh, yeah, the id_f just comes from the identity. So like I mean, you know what id is, I'm sure, but the law is written with id, so I'm just writing it with id, and in this case it doesn't make any difference whatsoever. But I'm just writing it in the same format as the property we're trying to test. So by proving both of these properties about a to and from set, you know that these things are isomorphic with each other. And then because of the Curry-Howard isomorphism, you know, sorry, let me put that on the screen here. Because of the Curry-Howard isomorphism, you know that A is equal to B. So if, you know, a left side of a function is equal to the right side of the function, that's an isomorphism, and they're equal in algebra. So basically what we're trying to do is prove that this is equal to this using the Curry-Howard isomorphism. Yeah, that's what we're doing. But you're 100% right. The use of id is extraneous here, technically. It matches the properties that I'm trying to test, so I'm just leaving them there. Hopefully you're okay with that. And then our type signature is going to be basically C to A, C to B, C to A, C to B, and then we need a C, and we're going to return a bool. Oh, but we need to be able to compare A's and B's. So we need a constraint eq A eq B. There we go. Everyone good? I feel good. Okay, so this time we're going to take another function, and we're kind of doing this just a little bit differently this time. So we're gonna say where whoops, I already forgot the shape. So we're gonna take another f, oop, Jesus. We're gonna take an f and a c. And then we're gonna get two new functions back again, and this is gonna be these two things. F. And just put undefined here. Oh, I'm dumb. Sorry. There we go. So you have to compose these functions apply to f such that you get a function c to ab, and then you can compare them. I had them backwards, that's all. Okay, so now I have this c, and I need to and A prime, sorry, B equals B prime. Okay. And then I'm gonna remind myself what this returns, C to AB. So we're gonna take a C to a B and a C and produce a bool. And again, we need the eq. Oop, not here, here. Eq A, eq B. And to be fair, I don't have to write type. I don't have to write the types of these functions, but I like to be in the habit of them. I typically don't work backwards like this, but I'm visualizing these types is in these two different files has been a little tricky, and like composing them and working backwards and then just making sure that the types are all the same and what I expect them to be, and then everything compiles just kind of, it's easier for my brain. So hopefully I don't look like too much of a scrub while I do this. I mean, I'm a scrub and that's fine. Eggs 3. And luckily this time we can see the types. So we need an extra set of these, right? Integer, 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 integer. If you're unfamiliar with QuickCheck, I apologize, but you'll kind of see what happens towards the end here, how this actually works. It's pretty cool. I'll explain it after I run it, just for those who aren't super familiar with it. You guys are probably more familiar with it than even I am, so. Okay. There we go. So basically what QuickCheck is going to do is it's going to go through all these properties with these types and then generate a bunch of random values and random functions to operate on all of these integers, okay? Specifically 100 in this case. That's the default. I think we can ask for more. I don't remember exactly how to do it, but I can look it up if people are interested. So it's going to just generate a bunch of random values for integers in this case, and then these bools and spin values from before, which I can show you the data types real quick so that you see the two types. So spin can be up or down, and a bool, as you probably know, is true or false. I'm gonna shut the door because my girlfriend's listening to the TV really, really loud, and I can't focus. Be right back. Okay. I was losing my focus there for a second, but I think we're okay now. Anyway, so this up-down thing, basically you have to make these arbitrary instances for QuickCheck. And what the arbitrary instances are just, they are literally just random values. So this says, when you create a gen object, which is one of these random objects, you can either make one of a gen up or a gen down. Okay, and it's chosen at random. So there are different functions you can use from QuickCheck to generate random values, but you need to have a specific type to make this happen. Okay, so anyway, we're gonna check this real quick, and then we are going to move on. If you guys have any questions about this particular set, just let me know. Otherwise, we'll just run this and keep going. Okay, so as you can see, we've passed all of our tests. So I'm not exactly sure why there isn't a new line here. It seems like it would be nice if there was, but I don't really know. Maybe it's worth finding this and trying to submit a bug patch, but maybe not. And I don't know where this new line would come in. Is this new line supposed to be in stack test, or is it supposed to be in, well, it's got to be stack test, right? Anyway, not that important. The important part is we got all this done. Okay. So next, what do we got next? We have a quick little section on canonical representations. Let's see here. A direct corollary that any two types with the same cardinality and two types with the same cardinality are isomorphic is that there are multiple ways to represent any given type. Although you shouldn't necessarily let it change the way you model types, it's good to keep in mind that you have a choice. Due to the isomorphism, all of these representations of a type are just as good as any other. However, as we'll see on page 168, so we'll do that later, it's often useful to have conventional form when working with types generically. This canonical representation is known as sum of products. So let me show you some examples of sum of products. Just so we're clear of what that means. I did this today, actually, and I did it on accident, but, you know, that's okay. So, sum of products means that the following are valid types. Not valid, that's not the right way to say this. They're canonical types. So let's call these canonical representation is sum of products. I'm gonna hit you with the math. T is capital sigma underscore m rho I think n t mn a b okay. However, wait, how is this different? Well, it doesn't show any of the... Well, it doesn't show any counter examples. So, let me create some less standard examples, I guess. So, sum of product is like right? Data product of sum is, how would we write product of sum? I guess how do we write product of sum? I don't actually know how to write it. I don't think this is valid syntax. I don't know how to write product of sum. Let's see if I can find an example on Google, because I don't know a good example. If anyone knows one, feel free to let me know. Product of sum Haskell example. You know why they're called sum and product types? Yeah, this isn't gonna work. I can't think of a good example. Maybe we'll look at one later. Oh, no, product of sum. No, that's a sum of products as well. Let's look at it. Product of, oh yeah, that works, right? So oops, this isn't the right syntax. Like this? Is that a product of sums? I think so. I think so. So how would we represent this as a sum of products, though? Would we say either let me think. Well, I mean, this is a bad example. B. What is this complaining about? Oh, right. And I can't call them AA. We'll call them primes. Just. Is this right? This is sum of sums, though. This isn't a sum of products. Yeah, I guess it. Yeah, it is. Yeah, these are product types. So this is a sum of products. We're not using either, but that's okay, I guess. Oh, yeah, we could do that too. That's a good idea. Yeah. I like that. So, one, well, something like this. Oh, but I need. Well, I need data constructor here, so for lack of better names, let's say something like this. And then let's put this here and that there. I think this is right, because this is a record of A that's a sum of products, I think. Unless I'm thinking about this incorrectly. I don't know if this is right. Okay, so anyway, the point is that you want to try and avoid this. Wait, no, that can't be right. Because people use records all the time. This can't possibly be right. Well, maybe the point is that you don't use records in this way. I don't know. We're supposed to get more of this on later in the book, so maybe we'll come back to this. Maybe I'll put a note here. A bit confused here. Supposedly clarified in. So I wonder if how we do this. Tree. Yeah. I think, yeah. Yep. That's correct. Supposedly clarified in, let me see what chapter that is. Hang on. 168. So I think what I'm going to do is write 68 is in chapter 13. Chapter 13. So I'm wondering if we should put some little okay, so here's what we need to think about. What I'd like to do is we're trying to make a reference back to this so that we can look back at it later. So do you think look back is a good name so I can go search for this later and maybe try and clarify this? I think this is right, but I don't feel super confident about it. Look back, help, maybe just help, to do. Let's just use help. Anyway, we can try and be careful about writing this. Although, yeah, again, there might be something that I'm missing here, which is okay. All right, so that's actually the end of chapter 1. So what we're gonna do is we're gonna make a quick git commit and then start a new project. So git status is just those two things. So git add git commit. So finish chapter 1. Clean up property QuickCheck properties. What else do we do? I think that's it. I don't think I did anything else. Probably good enough. Okay, so we've pushed that, and just for reference, actually, did I make a command for this? Forget if I made a command for this. So let's make a quick command called code. And let's put the GitHub code in here. What is it called? Thinking with types. Here is a link to the code we are working on. Bam. Save. Close. Yeah, so Ryan was here yesterday, and he was here earlier today. Hopefully he's still watching. And then Sandy followed, who is the author of the book we're working on, which is awesome. And then a buddy of mine, Joel. followed, so that's great. We also made a YouTube today, so if people want to go check that out, you can just write YouTube, and you can also write now code, and those are both links to the YouTube channel, which is new, and the code that we're working on if you want to check it out. Okay, so the next thing I said we were going to do is work on chapter 2. There's not a ton of exercises here, but we'll have a discussion, and I'll probably type some stuff in because this is something I'm not very familiar with. Some lightning. It's cool. I'm not super familiar with this, so we'll just call these exercises again. Why is this taking so long? I guess we'll sip of water. Usually doesn't take this long. So one thing about the YouTube, by the way, is if you're like just coming to the channel, you can just watch the things on Twitch, but eventually those are going to go away. So we're just going to go put stuff there when we, you know, as we complete videos. Maybe once a week I'll try and update videos there, but it takes a really long time to process them. So I trimmed the one today because at the beginning of on Tuesday's discussions, the beginning was me like setting up, so it was kind of a waste of time for you guys to watch it anyway. I should probably make one of these myself, right? Like my own style. But we'll see how this goes. I just used the plain, although maybe the plain one's probably a good choice because everyone's using that. I don't know. Okay, so in chapter 2, we're going to talk about terms, types, and kinds. So I said I was going to do this last time, so let's do it. Terms, types, and kinds. Chapter 2. Not that that's a big deal, but it would be nice to have some more in the README. I should probably update the README for chapter 1 just to explain how to run the code, right? Or at least put that in the top level README, but I can do that on my own time. Okay, so fundamental building blocks in Haskell are two things: terms and types. Terms are the values you can manipulate, and the types are the types that you're used to. They are just simply proofs to the compiler and to ourselves, so which I think is really important. The types for me make a big deal. Yeah, so they're proofs to the compiler that the programs we write make sense. That's kind of the idea. And that's sort of the Haskell, the two Haskell types. But then in the kind system, at the type level, I'm gonna just stumble over some words here because I don't know them yet. For type level programming, you use types and kinds. The types now become things to manipulate, and the kinds become the proofs we use to keep ourselves honest, right? So the types are analogous to terms at the sort of programming level of Haskell, the normal level that we work at, and kinds are equivalent to types, analogous, not equivalent. Yeah, so the type system for types. That's kind of the quote unquote. All right, so let's did I leave this open? Good. So let's look at an example just to give ourselves some idea here. Otherwise, this is pretty confusing. Let me delete this. We don't need any of this. And then delete this as well. Let's stir land flow. Probably won't need this. Whoa. B int 5. Okay, so we'll define some terminology, right? This is a type, this is a term, and the point is that a term you could replace anywhere, right? As long as these two things are both integers, you can put those values anywhere that you choose. It doesn't matter to the compiler whether it's a 4 or a 5. All it cares about is that it's an int. Yeah. By the virtue of both being int, they're interchangeable. Right? That's the point. Okay. And then the word type can be used to describe anything that exists at the type level, which is to say anything that is neither a term nor a kind. It's the kind of types that have inhabitants. Sorry, I'm just reading. Give me a second. I need to read this. I have to do a little bit more reading here than maybe we're used to. So one thing I'm curious about is if this has actually changed or not. Tuple I wrote. So he mentions in here that so when you look at a kind, when I import, oh fine, we'll just import lib kind. Right. Okay. Sorry. You can't write kind of a. You have to write kind of a type. But he was saying this star is actually older terminology and is going to get replaced in the latest version of GHC. It looks like that hasn't happened yet, but supposedly this is going to get replaced with literally type like this. Okay. Star and arrow. Yeah. So keep in mind that there are multiple kinds. So like if we look at the kind of maybe, there's basically a star and an arrow, right? So this is like waiting for something, something with kind star to create something with kind star. If you've never seen the kind notation here, let me make this a little bigger. If you've never seen the kind notation before, here it is. So in the book, this is written as type. In the book, this would be written as type to type. Okay? And then if you wrote kind maybe int, that would have kind star, right? Because you've given it this first kind, therefore you've given it the first star, therefore you end up with a single star. Something like this. Yeah, we're dropping viewers because this isn't so interesting. Which is fine. We'll do some interesting stuff later, I'm sure. Type to type. Either takes 2 parameters, right? So if we look at the kind of either, we have star, 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 right? Because it's waiting for 2 things. At the type level, this. Constraint is the kind of any fully saturated type class. Constraint is the kind of any fully... Oh, I see. Okay. So we're looking at this function. Well, it doesn't have the constraint here. How would I find this function? I think we need to go look at this function. Go find the source code. Getting very hot in here. Here we go. This is good enough. Okay, so this show A here is called a constraint at the type level. And show, the function, has kind what? It just... Okay, so this is confusing to me. So show int has kind constraint. What's the kind of show? I'm guessing it's supposed to be star star? Oh, star to constraint. Okay, that makes sense. If show int has kind constraint, then, you know, show must require a star and yield a constraint. Interesting. So that's kind of cool, actually. Okay, so next is the kind of... We should write this. Let's write this down. Okay, so that was actually an exercise, so we should write it as such. Exercise 2.1.3-I. It's only text, unfortunately. So if show int has kind let's write it like this because that's how it's written in the book. Constraint. What is the kind of show? Is star to constraint. It's all caps, right? Yeah. Okay, that's one exercise. Exercise 2.1.3-II. What is the kind of functor? Kind of functor. So I think functor, I need to look at info functor. Oh, well, shoot, it tells you the answer. So it's star star star, I think. This is a question. This is a question. So I'm pretty sure that K functor is going to be star star star. Shoot. That was close. But why is this a constraint? Oh, I see. Because functor, you don't write functor in your type signature, right? You would just write F. Functor is a constraint. That makes more sense. Okay. Gotta think about it like that. right, if you look at the type of fmap, right, functor is here. Yeah, exactly. So functor is not a type like A and F are types. It's a constraint, and it goes on the left of I don't. Does this have a name? What is this called? It's got to have a name, right? I don't know what it's called. Anybody know? I have a feeling that this is going to be nearly impossible to Google. Can I wonder if can you just Google it? I doubt it. I didn't think so. No, not gonna happen. That's fine. Okay, so the above is incorrect because functor isn't a type. It is a constraint. So kind functor star constraint. Okay. Exercise. This makes sense now that I think about it. It's just I wasn't thinking about it properly before. What kind of monad put two spaces in between these? Oh wait, no, just one is fine. V monad trans. I don't use monad trans very much, so I'm gonna have to look up the I of that. But monad is exactly the same as functor, so it should be just this. Well, not exactly the same, but behaves the same. Wait, is that right? I think that's right. We can look at info. That's apparently safe. Yes. It's going to be exactly the same, just that this becomes M. Yeah. So functor, applicative, and monad all have the same. Yeah, it's like you have like the do people say class constraint? I've never heard class constraint before. It's fine if it doesn't have a name. It's just I like things that have names. I don't know what monad trans looks like. Oh, it might be. This will discuss the constraint kind. I mean, they're constraints, right? Oh, okay. That's fine. I don't know monad trans, so we'll just look it up in Google. Actually, we need something that takes monad trans T, right? But that's not going to work. This will work, because this just means it takes star to constraint. And also we can figure out where this thing is. Control monad trans class. Import control monad trans class. Okay, we need transformers. Package 23G transformer. Okay, so yeah, I mean, anyway, now we can see that, and then therefore if you kind it, you'll see star, well, in parentheses, star, 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 star to constrained. Right? Perfect. Let's copy this and put it in our notes. So import requires control monad trans class kind monad trans is star to star, which is the monad. Star to, I don't know what these are, to constraint. Okay, so that's that. Okay, now we're gonna look around. We're gonna look at this data kinds definition. So let's add it. So here we have language data kinds, and then we will make our own data type so that we can look at the kinds. So if we write data, we'll use the spin because we had that before, up, down. And I think all we have to do is probably reload this. I don't know if these will be available. How do I find them? Do I write kind spin? Kind up? Is in scope. Did you mean data kinds? Yes, I did. How do I load this? Set -x data kinds. Reload. Shouldn't it have a tick? So we should also have this. Apparently we do. And they're of type spin. Okay, so this data kinds thing is basically what is the term here? These are promoted data constructors. So the promoted data constructors are built by default when you have a data type in with this X data kinds definition. So now we have these promoted data kinds, promoted data constructors up and down to play with. All right, so let me say this with an example in front of us. Okay, so if you had data unit equals unit, and you were using this data kinds language extension, you have to make oh, I need to put these under here. discussing data kinds language extension. I suppose you don't need to be capitals, but that's fine. So promoted data constructors are built. Tick up, tick down with kind spin. All right, so they just he makes a point here that you have to pay attention, because like when you have this kind of case, you have a promoted data constructor as well, tick unit. You have to be careful with all the terminology, right? Because you have a data constructor called unit. I'm sorry, a type constructor called unit of kind type. You have a data constructor, and you have a promoted data constructor, and this is of type unit. I'm sorry, of kind unit. You can see how the terminology gets hard to get used to. Well, it'll take me a little bit to get used to it. They said it's a subtle point and can often lead to inscrutable compiler errors. So while it's fine to ask for values of maybe unit, right? Maybe unit, it's a kind error to ask for maybe tick unit, because this is the wrong type, wrong kind. Ooh. This is the wrong kind. Wrong kind. Can we just like write that in here now? So we just wrote C maybe unit. C equals undefined. D maybe unit. Oh, that's, hopefully this fails for the right reason. Look at that. Okay, so the compiler will tell us this. Expected a type. So it expected a star, but it got kind unit, so that fails. That's useful. Because the kind of maybe is star star, or well, let's use the terminology that's apparently coming down the. Okay, cool. So I think this helps a bit. Writing it this way, I think, helps me a bit anyway. Hopefully it helps someone else. So it says, as we write more and more interesting type level programs, we'll use kind signatures to restrict the sorts of types we can be dealing with. Promoted data constructors are often are of the wrong kind to ever exist at runtime, which raises the question, what good are they? It's a little too soon to answer this in full glory, but without any other fancy type level machinery, we can use them as phantom parameters. Okay, so let's try that. So we're gonna build an application that uses this data type. Data user type equals user or admin. But then apparently later down the line, we've decided to do, I'm gonna have to write some notes here. User maybe proxy. I don't know what this proxy thing is yet. Admin. So we're missing some stuff here. So we need a data type for admin. Data admin. Admin. Does anyone know where this proxy function comes from? Maybe you'll beat me to it, but polykinded GHC. Is this the right thing? Or do we need, I feel like I read data typable recently. This one also has typelets. Let's try just data proxy, I guess. Import data proxy. Okay. And then we're gonna have a function that's like do sensitive things. Proxy admin. Okay, so this is the code that we're interested in. So the alternative to this, by the way, would be, I guess you would need to do something like this. User to IO, and then explicitly pattern match or something. I think the point here is that, what's the point here? This minor change will cause a type error whenever do sensitive things is called without an administration token. Such an approach makes it harder to accidentally call do sensitive things. Okay, so the goal here is to just not even call do sensitive things when you have a user. You only want to be able to do it when you have a just proxy admin. So you'd have to explicitly pattern match on just proxy admin to call do sensitive things in the first place. If you had a nothing, you could never use this do sensitive things. So I suppose you could have like a list of users, a list of maybe proxy admins, and then you could do something for all your admins. Like you could just fmap and you get that for free. So you can't call it on non-admin users or something. Anyway, it says there's more tricks about this later. So we'll talk about this later. Okay, so the next thing we need is import GHC typelets. I don't know what that means yet. Okay, so let's write some notes here. So if you use the user type, you can call sensitive things as a user. However, using the proxy, maybe proxy admin, can get a type error in trying to do sensitive things from your code as a user. How's that? That seems okay. Okay. Okay, so the GHC typelets library module defines all of the kinds themselves, as well as all of the useful type families for manipulating them. We're going to talk about that. But first we have to talk about some other things. The promoted version of a string is called a symbol. Symbols are not lists of characters. Symbol type literals can be written by using a string literal in a place where a type is expected. So as an example, let's go here. You can do things like kind of hello, and you'll see that this thing is a symbol, okay? But it's not like a list of characters like you would think for Haskell or a string. And apparently that is a frustrating thing, the fact that this is true. And the reason it's frustrating is you couldn't destruct it. So you couldn't say, like, what's the first character of this symbol? That's not a thing you're allowed to do. You can apparently append them. So you can write, like, kind append symbol import ghc.typelets. Yeah, there it is. So this takes two symbols and concatenates them, apparently. I've never seen this syntax before, but apparently you can do thinking with types. Maybe I have to explicitly write kind. Oh, duh. I'm going, why isn't this working? There we go. And so this is a symbol, and using a pen symbol, you can apparently pend lists together. Again, this is more information than anything, because we're gonna need to use this stuff later, I'm sure. So you can also compare symbols. Compare symbol. Those are, notice that this is a promoted type constructor, data constructor. It looks like they obey the greater than less than that from before. There are also natural numbers. Oh, that's kind of neat. So you can actually do math in the type system, but we need to set type operators set. Oh, you can't write S? I thought you could write S. Okay, so you can do kind. By the way, there's no floats in the kind system, but you can write natural numbers. 17 times 3. I don't know why that doesn't work. I'm not sure why this doesn't work. Maybe this is an error, or maybe I'm missing something. Can we write like 1 times 3? Oh, so it's something about the multiplication symbol. So something about the multiplication symbol that makes this not work. Apparently there's like even, you can even write things like div 1. There's no mul, right? What if we write something in like silly like this? I'm not sure why that doesn't work, but okay. So something's up with multiplication. There's also apparently lists that you can use. So you can, I think you can build lists by saying things like 1. Oh, I need to look at that. That's cool. So you can put like a tick in front of the cons operator and a tick in front of an empty list and make a list with just 1 in it, for example. You can also do this with booleans, but you need to be careful with your note. You can't have like a tick here. There has to be a blank space there. So if you wrote kind true it doesn't know how to do that, but if you just put a space here, it's okay. So I could see how that would be a little quirky and annoying, but I think it makes sense, right? Otherwise, like, how would it determine whether this is a, well, can you write a character, I guess? I assume you can write a character. You can't. I'm not sure. It doesn't say you can't. It doesn't say you can do a character yet, but okay. Apparently you can do this with tuples, so like 2, hello, or true, whatever. So you can make tuples. Do you guys say tuple or tuple? I guess it's tuple, right? I don't know the right answer. Okay, let's talk about type level functions next, because this, I think this might be at least a slightly more interesting problem. So I've never written a type family before, but this is how you do it. Or true. What? Oh, it's or. So I assume you probably can't do that, is why this is the case. Or false and anything is false. Oh. Wait, what? Oh, we need type family. This is pretty weird stuff. Families. Yeah. Still spelled it wrong. Okay. So this is a... Can I now use this on the command line? Keep doing that, sorry. So reload. So can I do kind? I'm guessing I need this. And I need two booleans, so true or false. Now, is that the right or? I don't know if I hope it's the right or, but we can just change the name to something silly, like stream. Can't. Oh, maybe there's a stream, but there you go. So stream. So if you don't, if you change the name and it fails, that implies that it's not just imported by default. So we're actually writing this. All right. So the next exercise is to write the type family for not. So let's do that. I don't think it's going to be very hard, but we'll do it. 2.4-I. Write the closed type family for not. So type family not x bool. I wasn't expecting this to work actually because he explicitly wrote y in here. I was thinking that maybe it would fail, but it... Oh, actually, right. Technically, this is not correct. Sorry. This is correct. Bool, where not true, false, oops, false, not anything true. So like so. Apparently H format won't screw with type families for reference, if that matters. I don't know if maybe stylish Haskell does or something. Maybe none of them do. Anyway, it says here that the metaphor between type families and functions is enticing. It isn't always correct though. The most important one is that type families must be saturated. So if you look at a map, like the map function or fmap function, like we were talking about earlier, you can write the map function as a type family, like so, but it doesn't work. So let's prove that it doesn't work. Yep. X, A, B, I, list A, list B, where map F empty list is empty list. Map F. How do you write? Wait, oh, no, this is not, that's not right. It doesn't say to use polykines, but that's fine. We can add that. So to do this, you need polykine. Type operators. There we go. Okay, so there's apparently a bunch of plugins you need, language extensions to make this work, but I suppose we're gonna. Oh, that is the promoted data constructor for the cons operator. So it's the cons operator in the kind system. Sorry, in. How do I say this? No, that's right. It's a promoted data constructor for the cons operator, and it has kind of the cons operator. Yeah. I think that's the right way to say that. Hopefully I didn't missay that. I think it's closed anyway. Okay. Now the point is that even with this, you can't write things like this. Proxy. I need to import data proxy. Hang on. Undefined proxy map or true false true. And parenthesis. Okay, so let's read this carefully because this is a little funky. So this proxy thing is a polymorphic type, so you can put anything in here, I guess. Hang on. Let me make sure I'm saying that correctly. Where's the first time we saw proxy? It may not have been explained in its entirety. But let me make sure because I don't want to tell you something wrong. There's no mention of this proxy yet, but I suppose we're probably going to talk about this more later. But anyway, so this proxy takes something, so it's this whole thing, and apparently this can be a polykinded thing. I don't know. But we're trying to map the function or true over the list true, false, true, as, again, all of these are promoted data constructors. I'm trying to use that terminology over and over and over again. But the proxy thing is still a little confusing to me, but that's okay. So this is going to fail, apparently, because you need to have full saturation. So you can't actually call recursive functions inside of a type family. So that was the point, is that it has to be fully saturated. Ow. Need to crack my back here. There we go. How much longer do we have in this? Okay, we're almost done with this chapter, so let's finish this chapter and then call it a day. It is 9:30, so technically would be the time I would get off. So this error is trying to tell us that we use the OR closed type family without first saturating it. We only passed it one parameter instead of the two it requires, i.e., right, this is a partial function. That's the problem. Oh, it doesn't even try to do the recursion. It's actually failing at the partial application of OR to true. Okay, that's kind of interesting. There's nothing preventing us from writing map, but its usefulness in this form is severely limited. We are simply unable to curry closed type families, and so we can't use map to perform any interesting type level computations for us. We will later explore some techniques for working around this unfortunate limitation when we discuss first class families in chapter 10. So that's coming, but for now we're limited, which is fine. Okay. Bring back this. It says, let's look carefully at OR. Okay, let's look at two more. They say let's look at these. So if we had type family foo x bool y bool and type family bar x y Okay, so this is weird. Okay, so we're trying to think of the kinds. So the question is, what is the kind of foo? Foo is, I believe, well, to be fair, I looked at the answer already, so I kind of know that that's right. Though kind, sorry, let me this up a little bit. It's kind of hard to read. Bar. There's something about the bottom of the screen for me. I don't like it in Visual Studio, but I'm okay with it in like Vim. I'm not sure why. Like if there was just the tiniest bit of space there, I would like it better. Not sure how I can explain that. Apparently this is type or star, but again, think about it as type. He doesn't capitalize them here. Right? So the thing on the right, sorry, I got a cough. The thing on the right of the double dots here, I don't know if this has a name either, but double colons, is the return kind. Return type. The terminology here is very hard for me. Yeah, the kind of the type that's returned by the type family. So the return kind is bool bool bool, and the kind of bar is type bool bool bool, right? This one is x bool bool return bool, so foo is bool bool bool. Okay, does that kind of make sense? Apparently, it disagrees. The actual kind system here disagrees. I'm curious. What is it? Oh, I'm sorry. It says that GHCI agrees with our assessment. I thought it said disagree. All right. So anyway, this is chapter 2. So we're actually done with chapter 2. So real quickly, let's see if we should add any more notes here. I definitely want to add a note here. So although this type family is written correctly, it isn't particularly useful because kinds must be fully saturated. In other words, a map or true we don't need to have more than 2 of them will fail because or is not fully, well, I'll just write is partially saturated. Okay. Let's see. Should we write anything else here? I think so. This is probably pretty good, right? Yeah, I think this is good. So let's commit our code. To terms, types, and kinds. Cool. So again, for everyone here, we're calling it a quits for the night, but we did finish a few things. So if you want to check out the code, here's the code. If you want to check out the book that we're working on, here's the book. I'll put it on the screen real quick. So it's here. So you can get the, this is the, oh my goodness, the ebook. If you want a physical book, somewhere there's a link, and I saw it earlier, but I'm missing it now. Where did I see this before? I don't remember. But you can get it at Lulu Book, not Lululemon. You can get it here too. Thinking with types. And I definitely bought it here, not the other place. So it's actually on sale right now. So you save a good amount of money. So if you guys have any questions, feel free to ask them before I get out of here. But we will be back on Sunday to discuss variance, which I think sounds really useful. So like the example they give is, or the first sort of motivating example is, given a bunch of these new types, which one of them or how many of them have valid functor instances? And apparently you can determine that by examining the variance of the type. So this sounds like super cool to me.